So here I'm just going to do a quick overview of what you need to know about derivatives for math apps. In math apps, you just have to know basically what the derivative tells you, how to do simple derivatives, nothing too complicated, and how to do tangent and normal lines and then optimization. So let's just type in some sort of funky looking equation, x cubed plus 3x squared minus 6x plus 1. And let's look at this puppy. So it's wiggling up and down and all kinds of things like that. What the derivative is it tells you the slope of the function at a point. So keep in mind that anytime we talk about derivative, we're talking about the slope of the function. A lot of times the IB will use the word gradient of the function. That just means the rise over run at a certain point. And so, for example, if I am looking at like this point right here, the rise over run is going to be pretty darn steep, and it's going up. If I look at this point right here, the rise over run is flat. If I look at this point right here, the rise over run is negative and steep. Here, the rise over run is flat again. So depending on where I put my point down, I will get a different slope because the curvy function is going up, it's flattening out, it's going down, it's flattening out, it's going up again. One metaphor is you just think about if you're skiing down a hill, your skis are tangent to the curve of the hill. Okay, that just might help you. So you're skiing along the function, and wherever your skis are going, those are flat, and that is just pointing in the same slope, in the same gradient as the function itself. Okay, the only rule that you need to worry about when you're doing a derivative in math apps is dealing with polynomials. In other words, dealing with a bunch of x's, powers, and numbers. And the rule is always, if you have something, x raised to the something, then the derivative is you multiply the power in front and you subtract 1 from the power. I could prove that to you, but we don't need to prove it to you. In math apps, you're just going to use that rule over and over and over again. So what that means is when I'm looking at my original function, I've got 3x squared. That means I'm going to do 3 times 1, because I'm bringing the power down in front, x raised to the n minus 1, 3 minus 1, 2. Then I go to the next piece. 3x squared, I go 3 times 2, raise that to the 2 minus 1. So I could type 1. I don't have to type anything because x to the 1 is the same as just x. Then I have 6x. Sometimes this trips people up. Think about what is the slope of 6x. The slope of 6x is just 6. If you want to use the formula, you're taking 1 times 6, and then 1 minus 1 is a power of 0. And a power of 0 cancels it out. It is equal to 1. X to the 0 is equal to 1. So to finish out our derivative, we go minus 6 there. You might wonder, what happened to this 1? Well, you can think of 1 as being 1 x to the 0. So when you multiply the 0 in front, it gets rid of it. Or you can think of the number 1 as being a flat line, so that has a slope of 0, meaning it adds 0 to the derivative. Okay, so that was just an example of using it. You can do that on any polynomial. You take the power, multiply it in front, subtract 1. That's how you get the derivative. So now it can be really confusing when you look at the graph of the original function, red, and the derivative, which is in blue. I'm going to make them a little bit wider. What I want you to remember is that the blue function is the derivative, the red function is the function. So every time the red function is going up, so if I grab it right here, along this zone here, the red function is increasing. So the red is increasing. It's going up and to the right. And what I want you to notice is that in that same exact zone of x values, the blue is positive. Because when a function is increasing, another way of saying that is its slope is positive. Then I want you to notice what happens next. From here to here, the red function is decreasing. And in that exact same interval of x values, you'll see that the blue function is below the x-axis. The blue is negative. Wherever your derivative is negative, that means your slope is negative, that means your original function is going down and to the right. And similarly, after that point, you see that the blue function is positive and the red function is increasing. The further away from the x-axis that your derivative is, the steeper your function is. The derivative is how much slope does your function have at that same x value. So if I look right here, at this x value, the derivative is approximately 10. And what that means is at the same x value, the red curve has a slope of about 10. If I go right here, the blue function, the derivative, has a slope of 0. And what that means is at that same x value, negative 2.7, the red function has a slope of 0. It doesn't have a y value of 0, but it has a slope of 0. If I tried to draw a tangent line to the red graph, that would have a slope of 0. Right here, slope is 0. What that means is our derivative is equal to 0. Here's the notation for derivative. There's two ways you can do it. You can write it as dy over dx, which is just saying change in y over change in x. Or you can say f prime of x when you're talking about a function. Both of those just mean that the slope is 0 at that point. So keep in mind, if the derivative is positive, your function is increasing. If the derivative is negative, your function is decreasing. If the derivative is 0, your function is neither increasing nor decreasing. So that brings me to optimization. Now, optimization is just a way of saying finding the maximum or the minimum value of the function. And you just have to read the problem to think about which one they want to give you, you want to find. Sometimes they'll say find the smallest possible surface area. Sometimes they'll say find the biggest possible profit. That just means trying to find these locations on your original function where the slope is 0. In other words, that just means finding out where your derivative has x-intercepts. You can do that on your graphing calculator, type it in. You type your derivative in, type your function in even, and find where your derivative hits y equals 0 using the 0, finding the 0 thing. So that's optimization. Sometimes the hardest part about optimization is you have to work to get the right formula. Maybe you have to substitute one thing into another thing to get the right formula. But at its core, whenever you read optimization, whenever you read a problem that says find the maximum or the minimum, or find the biggest or the smallest, you should think, can I make the derivative equal 0? Okay, and then you can find it that way. All right, the last thing that I wanted to touch on were tangent lines and normal lines. So the derivative is the slope of the tangent line. So like, let's say, for example, that I wanted to find the equation of the tangent and the normal. So let's do two different curves. Let's say I want the tangent and the normal, and then I want both of them when x is equal to 3. Okay, so to find the tangent, what I'm going to do, so I'm going to do x equals 3 for both these problems. What I'm going to do to find the tangent is I'm going to plug in 3 into the derivative. So here I have my derivative, and so I'm just typing in the derivative, and I plugged in 3. See how I typed it into the derivative equation there? And I got 39. So when x equals 3, the tangent has a slope of 39. And the normal has a slope of, well, what does normal mean? I don't even think I told you that. Normal just means perpendicular. So the normal has a slope of opposite reciprocal. Okay, so that means that my tangent line, you can either do point slope form or you can do mx plus b. I've noticed a lot of people like to just set up mx plus b and go for it. So for the tangent line, you know it's y equals 39x plus something. For the normal line, you know that it's, oh, I chose the wrong pink, y equals, not 39, the opposite reciprocal. -1 over 39x plus b. So how do you get the b? You just got to plug in an x and a y value. We said that x was equal to 3, so let's get the y value by using the original function. So I typed it into the original function there and I got 37. So I take x equals 3, y equals 37, and I plug it in. So if I do the red one, I'm going to get 37 is 39 times 3 plus b. 39 times 3 is 117. 37 minus 117 tells me the b value. Oh, come on, don't fail me, pen. The b value is -80. Real similar process for the other one. I go -1 over 39 times 3, because 3 is my x value. And then I go 37 minus the answer I got. Came out to be some pretty nasty decimals. So for the pink one, I just did 37, -1 over 39 times 3 plus b. We got b equals 37.08. Oh, my pen is messing up. Okay. So let's type in the tangent and normal lines, and you'll see how they look. Y equals 39x minus 80. I'm gonna make that, yeah, that looks good. So notice that when x is equal to 3, let's turn off the blue one for now. When x is equal to 3, that green line touches the red line. Let's see. Where am I? I'm missing 3. There we go. So right here at 3, the two graphs touch each other just barely. Come on, intersection. They're so close to each other, you can barely even tell them apart. Yeah, see at 3, 37, the two graphs touch each other, and the green graph is going in the same direction as the red curve. And then the other one, -1 over 39, x plus 37.08. You can see that that also touches it at the same point with just a little rounding error, and it's going and it's hitting it at a right angle. The tangent line just uses the derivative slope as is, and the normal line flips it over. All right, there you go. Thanks for watching.